We're now going to look at two different circuits in the time domain: resistor-inductor circuits, RL, and resistor-capacitor circuits, RC. This is in order to gain a deeper understanding of these components. Starting off with a basic RL circuit shown here. Note, this circuit has a DC source, meaning there is no frequency component. While it is a fixed voltage, note that initially there is no voltage drop over either component. The voltages over the resistor and inductor will only change when the switch is closed at time 0. The voltage across the resistor is equal to the resistance multiplied by the current. The voltage across the inductor is equal to the inductance multiplied by the derivative of the current. Using KVL, we know that the sum of the voltages around a closed loop is equal to 0. For this single loop circuit, this results in the following differential equation. The total voltage is equal to the resistance times the current plus L times the derivative of the current. We can then solve the differential equation to give us the relationship between the current in the inductor and time. I want to pull some important observations out of this equation. If we graph the relationship of current versus time, you can see as time increases, the current through an inductor rises from its initial value of 0 and asymptotically approaches V on R, which is the steady state. The time constant, denoted tau, is the time at which R on L is unity, that is, 1. Thus, for the resistor-inductor transient, the time constant is tau equals L on R seconds. That means at 1 tau, the current is 63.2% of its final value. The important takeaway from this is that for inductors, there cannot be an instantaneous change in current. It simply cannot occur. The inductor gradually gains and loses current to a point of equilibrium in line with this curve and corresponding time constant demonstrated. Now taking a basic RC circuit, we can perform a very similar analysis. Again, while we are dealing with a fixed voltage, the voltage and current over the resistor and inductor will vary when the switch is closed at time equals 0. The voltage across the resistor is equal to the resistance multiplied by the current. The voltage across the capacitor is equal to 1 on the capacitance multiplied by the integral of the current. Again, it's known that the sum of the voltages around a closed loop is equal to 0. This results in the following differential equation. The total voltage is equal to the resistance times the current plus 1 on the capacitance multiplied by the integral of the current. Differentiating through, we get 0 is equal to the resistance times the derivative of the current plus the current divided by the capacitance. The solution to the differential equation is as follows. Applying this expression, we can get the following expressions for the voltage across the capacitor as well as the voltage across the resistor. If we again graph the relationship of the voltage versus time, you can see as time increases, the voltage across the capacitor rises from its initial value of 0 and asymptotically approaches V, which is the steady state. You can think of this as charging. The time constant, denoted tau, is the time at which 1 on RC is unity, that is 1. Thus, for the RC transient, the time constant is tau equals RC seconds. The important takeaway from this is that for capacitors, there cannot be an instantaneous change in voltage. It simply cannot occur. The capacitor gradually gains and loses voltage to a point of equilibrium, in line with this curve and the corresponding time constant demonstrated.